All right, hello everyone. Welcome to Best Practices for Scalable Monitoring. My name is Kevin Scaldaferri. I'm a software engineer at New Relic. I'd like to just give people a quick summary of what we're going to be talking about, just to make sure that you don't feel like you're expecting one thing and got another. So this is, use the word scalability here. I'm not going to be particularly talking about scalability in the high volume or high performance sense in this talk. Rather, this is going to be a talk about scaling your monitoring to keep pace with the growth of increasingly complex modern architectures. So this is a talk that I think the people who are going to get the most out of this are people who are in one way tasked with making their organizations more effective during this sorts of growth. So you might be a manager who's looking to reduce the toil that your teams are experiencing as they try to effectively manage a host of microservices. You might be an architect who's developing standards for your organization as they undergo a digital transformation. Or you might be a DevOps engineer who's responsible for building the tools that are going to accelerate the velocity of your organization. So why am I here talking to you? I'm actually not coming to you as a monitoring expert per se. Rather, I'm actually here to share with you some of the lessons that we learned at New Relic scaling a rapidly growing organization. So I'm going to use examples using New Relic, but that's because that's what we use at New Relic to do our monitoring. And I think it is valuable to have some concrete examples. So the story of New Relic, we've been around about 10 years. And we started, like a lot of companies, in 2008 with a monolithic Ruby on Rails application. Shortly after that, we spun out some of our back-end data ingest and data processing into a monolithic Java application. We were running single monolithic relational database, and we were running everything in a single geographic region. A lot has changed over those 10 years, though. And today, we manage dozens of front-end applications. Those are backed by hundreds of microservices. Data is stored in hundreds of small databases of various types, and we're deployed across multiple geographic regions. And it's not just our production infrastructure which has changed radically over this time. It's also the structure of our engineering organization. So in 2008, it was just a single small team, all located in the same office, talking with each other all the time, having lunch together every day. And it was very easy for everyone to kind of stay on the same page about how they were going to do things. But today, we have dozens of engineering teams, and they're spread out all over the world, and keeping that sort of consistency is more challenging. So back 10 years ago, with these monolithic applications, deciding to monitor them and going about monitoring them was fairly easy. In fact, most things about operating a monolith are fairly easy because you only have to do them once, and that's simplifying. So you would pick a monitoring provider that you wanted to use, go head over to their install pages, download a jar, install a Ruby gem, set up a basic config file, and you would be up and running with monitoring in no time. You could go and you could start poking around UIs, you set up some dashboards and set up some alerts. This was all pretty simple, straightforward to get up and running. In the microservices world, though, you definitely don't want to be going through all of those steps, all of that manual process every time you create a new service. But if you don't monitor all of your services consistently, there's going to be pieces that you miss, and you're going to have blind spots in your monitoring. This is really important because in the world of modern architectures, distributed tracing is rapidly replacing traditional profiling for understanding our systems. We can no longer limit ourselves to viewing just the internals of one application at a time. Instead, we need to be able to trace a request through all of our systems with views like this that are showing all of the complex interactions and subqueries that are happening simultaneously just to service that one request. And these traces can get really big. They can end up involving hundreds or even thousands of services and instances of those services. So if you don't have everything within your architecture monitored consistently and set up for this sort of tracing, that graph's going to fall apart and you're going to miss essential pieces of what's going on during your requests. So you're going to have to be a lot more thoughtful about your monitoring strategy for modern applications in order to make sure that everything's monitored and monitored consistently. Autonomy is one of the big themes in the industry today. And at New Relic, we are big fans of autonomous teams. But there are some places where you need to maybe put a damper on autonomy a little bit. And this is one of those places where you may need to rein it in and establish some standards for the sake of the greater good, and so that all of your teams can work together successfully. And when you're setting up monitoring in a modern architecture, it's going to end up touching all of the parts of your software lifecycle. So you're going to be incorporating it both as you're writing code, in your build systems, in your deploy systems, and then in, of course, the monitoring and alerting that you set up once it's in production. So in all of these cases, what's really essential is making the right thing to do the easy thing to do. Your engineers are going to be doing this hundreds or thousands of times. And that's a lot of opportunities for someone to either take a shortcut, skip a step, to make a mistake in one of those steps. And to avoid that, automation and consistency is really crucial. So we're going to walk through some concrete examples and some recommendations in each of these areas about how to achieve that. So let's start by talking a little bit about build systems. Modern build systems are extremely powerful, and you really want to take advantage of that power. This wasn't always the case. 10 years ago, I think most developers were writing their build files in languages which were unrelated to the languages that they were actually writing their applications in. And that is something which has really changed dramatically over time. And today, it's much more the norm that we automate our build processes using the full power and expressiveness of the programming languages which we write our applications in. And what that means is that we should be managing the code in our build scripts in the same ways that we would manage the code in our applications. So an example of what this means, here's some instructions for how to upload source maps after you minify your JavaScript when you're releasing a bundle. And if you're not a JavaScript developer and you don't know exactly what that means, that's okay. In all of these examples, the specifics aren't going to be really essential. It's more about the general concepts of what we're talking about. And so, anytime you see a set of examples like this, what you should immediately be thinking is, how do we do this automatically? Because what you don't really want is to rely on your developers going and manually uploading these things via a UI every time they do a release. Instead, the approach you want is to find the API and to code against that in your build system. Or better yet, pull in some reusable code that someone else already wrote. So in this case, there's an NPM module that you can get and that you can tie into your build and release process with a little bit of code like this, and it will completely automate this task for you. Let's look at a little bit of a more complex example. So these were the same instructions that were on a previous slide about how do you install the New Relic agent into a Java application. So how would you go about automating this process? I'm going to use Gradle as my example build system here because this is what we use at New Relic. But if you're not familiar with Gradle, again, don't worry too much about the particulars. In general, I find that you see a lot of build files where people just dump all sorts of stuff into them willy-nilly without a whole lot of organization or thought about maintainability. So in that approach, if we were going to do that here, we would just start writing some Gradle DSL. So we would add in a couple of jars, the compile time jar, the runtime jar. You'd write a little copy task that puts stuff into the right place when you're packaging up for release. You'd configure some extra arguments for when your run command to start up your JVM. And then you would still need to do a little bit more with the config file, but I'm running out of room on this slide. And the point is, although this is not horrendous, this is not a ton of code, this is still not really the approach that you want to be taking, where you're putting this into all of the build files for all of your applications. You don't want to make it so that every time that you start a new application, you have to copy and paste this stuff. If you think about it, you would not go about writing your application code in this way, and you shouldn't be writing your build scripts like this either. So instead, this is what we have build system plugins for these days. So everything that was on that previous slide can and should be done in a plugin. So you can find there's a couple of these out on Maven Central, or you can write your own. As we saw, it's not a whole lot of code to do this. So this is an improvement, definite improvement over the previous approach, but this is still not ideal. This is still some amount of boilerplate that you need in all of your applications, and including probably in those configuration sections that I've elided, and that's repeated code that you don't want to have everywhere. So if you want to change those things, if you want to change standards, you're going to be stuck going and changing this stuff in config blocks in hundreds of build files. So that's not great. To avoid that, the approach that I like is to actually create a mega plugin that actually pulls together all of the other plugins that you want to use, and you can provide them with sensible default configuration, and you can get to the point where individual services just apply that plugin, list their build dependencies, and that's it. So this creates a really nice looking build script, and it's really like much more the approach that we would take if we were building a modular software in our applications. And now when you make improvements to your standard processes around monitoring or around anything else, teams just need to update their version of that plugin, and they get all of those updates. So again, I don't want people to get too hung up on the particulars of specific languages or specific build tools. But what I do want you to do is to think about how in your systems you make it really dead simple for application developers to make sure that their applications are monitored. So you want to get into this world where monitoring is just the default. There's no effort that needs to go into it for any applications that are being deployed out into your production environment. Let's talk a little bit next about the role that deploy systems play in your monitoring. In this section, I'm going to take it as a little bit of a given that you already have a common automated deploy process. This doesn't necessarily have to be a continuous deployment system, but something that's standardized, probably centralized, way that you get all of your code into production. And if that's not the case, I would highly recommend that you look at addressing that before you go any further. If every team in your organization is pushing code out with their own Snowflake processes, it's going to be very hard to successfully monitor across all of them. There we go. The next thing that you want to do once you have something deploying your software is to be able to know what you deployed and when. When something changes in your monitored data, the first question anyone asks is, was this related to a deploy of something? And there's two general ways that you can track this information: deploy markers and version tagging. And they're both useful to have. This isn't something that you should consider an either-or choice. This is really something that you want to have both of them available. So to explain the difference, a deploy marker is a sort of an event log which gets recorded somewhere off to the side of your primary telemetry data. And they're nice because you can look at all of them. You can get a chronological record of everything that's changed across all of your systems. And it's fairly easy for charting libraries to go ahead and automatically display them on all your dashboards, give you like those little red lines or whatever format you like, so you can see, you get a hint that there was a deploy that happened. And recording them is generally a pretty straightforward matter of just making a REST API call as part of your deploy process. But there are a few things which are a little bit difficult to figure out with just deploy markers. So with techniques like canary deploys and phased rollouts and blue-green deploys becoming increasingly the norm for modern architectures, it becomes a little more difficult to know exactly what a deploy marker means. Is it indicating the start of a deploy, or is it indicating the end of a deploy? How would you represent events like when you start a deploy and you get halfway through it and discover a problem and then decide to abort and roll back that deploy? So for those sorts of situations, version tags are there to help you out. So this is an example of a dashboard where we've taken all of the telemetry data coming out of one of our systems, and we add a dimensional attribute, a tag onto all of them with the version number of the application running on each instance. So this lets us start by, we just look at how many instances of an application are running, and we can watch that increase over time. So this is a phased rollout that takes about 90 minutes. And then while that's happening, we can be comparing performance metrics on our application. And we'll see things like this. So we see that there was a little blip of warm-up time when the new version first got deployed out. But then after that, the two track very close together from minute to minute, even though the value of this metric is actually jumping around due to changing workload. And this is an extremely valuable thing to be able to do, to overlay graphs like this, particularly if you're running systems which are subject to large external shifts in usage. So when a metric changes in the middle of a multi-hour rollout of a deploy, you need to be able to tell the difference between one of those exogenous changes and a change that's caused by the code in your deploy. So you can and should use the same technique for other pieces of information as well. When we're called on to respond to an incident or to a support request, we frequently want to know the scale of a problem. Is it restricted to a single scope, or is it something that's widespread? So depending upon your architecture, you'll likely want to be able to compare or to restrict data based on isolation zones like clusters or cells or regions or availability zones. We also frequently inject host names into our containers because in the modern containerized world, our applications have generally lost the ability to actually introspect the physical machine that they're running on. And this can be a problem if you know that you need to shut down a misbehaving instance, but you don't actually know where that container is running. And then there may be other things that you want to track for whatever reason within your system. So for example, we sometimes like to know what team owns an application because this would let us do things like roll up CPU usage or other resource usage across teams. Regardless of the specifics of your system and exactly what those valuable pieces of information are for you, the critical role in your deploy system is to make sure that you have all of the information that you need to know exactly where your monitoring data is coming from. What version of what application, running on what machines, in which region, and so on. So might seem like we've gone a little bit out of order here, but we now have some of the foundations that we need to actually come back and talk about what it looks like to automate and scale monitoring within your applications themselves. So earlier, I touched on the importance of eliminating as much boilerplate as you can. But the truth is, you're never going to get rid of all of it. So if you do have to copy and paste some boilerplate to create a new service, that's something that you should at least make a machine do for you. So this could be using something like Maven archetypes or Rails app templates, but really any templating system can be made to work for this. And the big benefit that you get out of using Bootstrap templates is that if you keep them up to date with your current best practices, your overall microservice architecture will tend to drift in that direction. And this is the opposite of what happens in the approach where when teams want to create a new application, they just copy everything from an old application and do some search and replace and pull out the guts and put in new guts. When you follow that practice, that tends to lead to teams getting further and further out of date from your current practices. So we said a little earlier that your deploy system should inject environment variables describing exactly what's running and where it's running, but that doesn't really do any good unless your application actually does something with this information. So this is an example of what we would typically do to set up a simple wrapper library around any monitoring that we do so that those attributes get consistently attached to all of the data that we collect. So in this case, if we're recording a custom monitoring event, we would take the attributes specific to that event, but then we go and we just pull out of those environment variables all of that standard information that we want to have available later when we're looking at this data. Now, modern architectures have a lot of moving pieces and a lot of connections between those pieces. And that's a lot of places where you can potentially have a bottleneck. But if you're going to successfully operate these systems, it's really critical that you be able to identify and monitor those bottlenecks when they happen. So, I think that it's more or less a given that everyone monitors high-level utilization metrics like CPU and memory usage right now. But that's really far from the end of potential bottlenecks to keep an eye on. And really, the critical point is that any potentially exhaustible resource within one of your applications or in your infrastructure needs to be monitored. So inside applications, the common examples of this are things like thread pools, or connection pools, or memory pools, or anything else which ends in the word pool. And then the other big general class of exhaustible resource is queues. And that can get a little bit tricky sometimes because queues are often hiding in modern frameworks in places that aren't obvious. So in reactive or actor-based frameworks, we generally end up replacing traditional thread pools with queues or mailboxes, and it's essential that you keep an eye on those as well. In some cases, this might be made really easily available for you to plug into your monitoring systems, and in other cases, you might need to create some wrappers like we saw before. Either way, it's really essential to keep an eye on these, sort of like looking for your keys. Somehow the bottlenecks always seem to end up in the place where you hadn't actually put any monitoring yet. So, and the approach that we've generally taken to this, again, is to create sort of a standard structure that we're going to use to record all of our utilization metrics and how much they're being used at any given moment. And then we allow libraries to plug into that to provide that data, and then we can go and we can view across a whole system what the most constrained resources are at any given time. So the big goal there, and in all of this to strive for in the code in your applications, is consistent monitoring. So consistently tracking resource utilization so that you can easily see where your bottlenecks are. Consistently tagging all of your telemetry with the attributes that you'll need to locate where problems are happening. And keeping a general enough structure across your applications to enable you to make fair comparisons of the data that you're collecting across your entire architecture. So now we're at a point where we have monitoring data coming out of all of our services, but that's not going to actually do you much good unless someone's looking at them. So back in the monolith days, it was mostly good enough you could jump into the UIs and start creating dashboards and setting up alerts from there. But that's not going to scale well for large modern microservice architectures. It's too repetitive, it's too error-prone, and it's too hard to keep everything up to date across all of these systems. So in the modern world, generally people have gotten on board with APIs as first-class alternatives to those UIs. And from there, inspired by the infrastructure as code movement, we've started to explore what it might mean to have a concept of monitoring and alerting as code. So that means taking those APIs that you have, whether they're for creating dashboards or for defining synthetic monitors or for creating alert conditions, and going and building higher level control structures on top of them. Because if you think about an API by itself isn't really an improvement over a UI. I mean, obviously, we don't want people to be manually typing out JSON payloads and sending them in with curl commands either. That's actually more error-prone than going and using the UIs. So this is where DSLs, domain-specific languages, start to come into the picture. And DSL is one of those terms that can describe a lot of things. Essentially, what we're saying here is just anything which is capable of driving an API in an automated fashion. Whether that's a collection of scripts, some sort of templating and config language which has limits on its expressive power, or a full-blown Turing-complete programming languages. And we're going to now take a look at a couple examples of all of those sorts of DSLs. So this first one is an example of the scripting approach. So this is a command line tool that IBM built and put up on GitHub, which they use to help manage their monitoring and alerting. And this gives you a slightly nicer interface than curling raw HTTP commands. And it's something that you can use to start building more complicated workflows on top of. Something which I think is really valuable here is that it can also download all of your existing configuration. So IBM initially created this functionality for backup and restore processes, but it also means that you can easily bootstrap monitoring your alerting programmatically, and that you don't have to start completely from scratch when you're doing this. We do something internally at New Relic to manage our synthetic monitoring scripts this way. And this starts to get us into the subject of templating. So synthetic monitors are just little JavaScript programs, but they're going to need to know some things like URLs or API keys, which might be different if you're monitoring across several clusters that are providing a service. So in this case, we decided that we would make these scripts into ERB templates, which would allow us to do substitutions. And now we can have something that drives this where we loop over all of our configurations, generate a version of the script for each of them, and then upload that automatically via the API. We do something very similar with our dashboard management. So we'll start with the JSON representation of the dashboard in the API. In this case, we've gone and we've enhanced that using the Twig templating language. Although the details of the format or which specific templating system that you use aren't super important. But I wanted to let you see how this lets us iterate over sets of substitutions in order to maintain multiple dashboards with a similar structure. So in this case, the team that created this particular template, they wanted to have separate dashboards for each of the clusters of their system. If you're wondering about how we make use of all of those other attributes that we tag the data with, this little section here is what lets us take advantage of those. So this is just something that creates a general filtering control on the dashboard where you can now go in and you can filter down on any of those attributes that you set previously. So if I wanted to take a dashboard that's looking across our systems globally, I could go and I could filter it down to just the blue cluster in the US East 1 region, for example. This is Terraform. This is my next example, and this is an example of a configuration language. So this is a little bit different from the template languages that we were just looking at, because now we no longer work with the raw API format. Instead, we're working with something which is abstracting away what the underlying configuration uses, whether it was JSON or YAML or XML. Instead, Terraform uses this a declarative config language. It's called the HashiCorp config language, or HCL, which gives you this fairly clean way of configuring your alerts along with your other infrastructure. So out of curiosity, are many people using Terraform already? Yeah, pretty good number. Terraform is a pretty nice system. It's very high quality, it's well maintained, it's well documented, and it has a lot of integrations like this. And this is used by a lot of our teams at New Relic, particularly the ones who are already using Terraform in order to manage, to manage their infrastructures, the operational teams. For them, it makes a great deal of sense to also use the Terraform provider in order to monitor that infrastructure. We do find one or two downsides with Terraform. One thing that's just a little gotcha to watch out for is that not all of the Terraform resources support importing existing configurations. So you want to double check that if you're trying to migrate from existing monitoring and alerting into Terraform. You might have to start some stuff from scratch, unfortunately. And then the other thing that can be a little bit of an annoyance is that while Terraform does have some functionality for reuse via modules, at the moment there's no support for loop control structures. That is about to change when Terraform 0.12 ships. But at the moment, if you're trying to configure large numbers of applications and clusters, your Terraform config can get a little bit repetitive. So for that reason, some of our teams at New Relic who aren't operations teams but are more traditional application development teams, they typically prefer to use a Ruby DSL, which we've developed for managing alerts. So here's a simple example of what this looks like. This is Ruby code, but at this level, it doesn't look very different from the Terraform HCL. It's a very straightforward declarative configuration. Where things start to get a little more interesting is in examples like this. So because this is all Ruby code, we can add loops and we can add function calls and so on. So in this case, we're looping over all of our clusters, and then we use that cluster identity in a couple of different ways in the alerts that we generate. So the simplest one is that we're just inserting the cluster name into the alert policy. But things get a little more interesting from there. We can also do things like selecting notification channels based upon what cluster. And the reason you'd want to do that is that when something goes wrong in one of my production clusters, I want that to go to PagerDuty and page someone. But if something's going wrong in a pre-production cluster, I would typically only want to get an email or a Slack message or something like that. In the name of the cluster, there's another interesting thing that we're doing. So one of the things that we've learned over time is that when someone gets woken up by a page at 3 in the morning, sometimes it takes a few minutes for them to remember exactly how severe that particular alert might be. So like a lot of companies, we have an established set of criteria for determining the severity of an instance or of an incident. We use a scale from 1 to 5. And a trick that we've adopted in our alerting is to go through in advance and determine that, for example, if this alert triggers, that's indicating that we're in a severity 3 incident. So now we can put that, embed that into the message that the on-call responder gets when they're paged, and they know immediately what severity of incident to declare, and they just get a little head start on the response in that way. Again, we actually make this a function and feed in the cluster name, because in pre-production environments, it's not actually a severity 3, it would just be a warning or something like that. And then just another little kindness to your on-call responders that I wanted to point out in here is the runbook link. So it used to be the case that when someone would get paged, they would go and they would have to look at which application was alerting, then they'd have to go and find the docs for that application, find the instructions for responding to alerts, try to match up the alert that they just received with a list on that page. Hopefully it's actually there, and then follow the link to the runbook for how to respond to that. So that's a lot of steps, again, when you've just gotten woken up by a page at 3 in the morning. So we try to make that a little bit easier for people today by including a direct link to the relevant runbook in every alert. If you want to take even a little more toil out of the process of setting up your alerting, we can consider making the machines work for us again, and applying some machine learning techniques to creating alert conditions. So I'm just going to show examples here. So this is an example of a baseline alert. So in this case, rather than going and, traditionally you would set an explicit fixed threshold for an alert to go off in your condition. But in this case, we pick a metric that we're going to alert on, and we pick a sensitivity, and then it's going to go and apply some machine learning algorithms and automatically detect when there's an abnormal value of that metric. And this really aids in removing some toil from your teams, because this baseline will automatically take into account seasonal variation and organic trends in the metric, so you don't have to be going and sort of constantly, periodically recalibrating those alert thresholds. Outlier detection is something similar, but it goes one step further to pick out a single instance of a service or a single piece of hardware which is out of line with the rest. And this is really valuable because in a large modern deployment, a signal like this might be completely washed out if we were just looking at the average over all entities. So these last two slides, I've hopped back into showing you UIs simply because it makes it much easier to explain what these types of alerting conditions are. But I do want to say, these are still things that you can manage programmatically, and I would recommend that as the long-term scalable approach once you sort of get a sense for those sensitivities that you want to use. Again, what's important here really isn't the exact details of how you go about doing this, which one of these approaches that you want to use. It's the general principle of really automating your alerting across all of your system. Because there's really nothing that keeps your ops and DevOps teams up at night, like wondering if everything is actually being monitored, or if there's something that might be silently breaking and they don't know about it. So regardless of what techniques you use, having a consistent approach to generating and alerting on monitoring telemetry gives your teams the confidence that they need to be able to keep moving quickly. These sorts of infrastructure as code inspired approaches are exactly what you need in order to give your teams that boost. One more thing that's really important to do to keep that confidence up is that you should probably be, on a regular basis, actually syncing these configurations up to your system, up to production. And the reason for that is that you really don't want to get into one of these situations where someone went and turned off an alert in the UI one day for whatever reason. They probably had a good reason that day, but then they forget to turn it back on, and then it turns out that you're flying blind again. So once you've got your monitoring in code, set up something that maybe once a day or so on goes and checks that you've actually still got the alerts and monitoring that you were expecting. Okay, so I'm going to start wrapping things up. So we've walked through how monitoring for modern architectures at scale impacts your entire DevOps process. Writing and building code, packaging and deploying those applications to production, and monitoring and alerting on those systems. Across all of these areas, the common pattern boils down to three things: planning, automation, and simplicity. You want to start by thinking about the questions that you're going to need to ask about your systems. This won't necessarily be a one-time activity. You'll undoubtedly end up revisiting this over time as your systems evolve, but each time you do, you want to ask yourself about what information you'll need for your operations, for doing capacity planning, for responding to support requests and incident response, and for making business decisions. Then you want to automate the collection of that data through tools and libraries, and automate being able to view and alert on that data. Finally, make sure that all of your processes support doing the right thing, to the point that it's easier to do the right thing than to do the wrong thing. Because once you reach that point, you're going to unlock a freedom for your development teams to know that they're supported by the monitoring and alerting that they need, and that they can stop worrying about that, and that they can focus on building products instead. All right, so thank you all for coming this afternoon. Once again, my name is Kevin Scaldeferi. You'll find me at kscaldef at most places on the internet. I know people might need a little bit of travel time if they're heading to another venue after this, so I'm not going to hold everyone in the room doing audience questions, but if you'd like to talk further, I will hang out until we need to clear the room for the next talk, so feel free to come up and chat. Thanks.